Welcome to Season 2 of the Coherence Times, where we bring coherence to the entangled world of quantum computing. I'm your host, Ryan Mandelbaum. Every other week, I'll bring stories about how scientists, developers, and businesses are making quantum computing a reality. We'll explore the latest research and development, highlight new advances in the field, and see how users are trying to extend quantum to real-world use cases. Now, this year marks a special milestone in the history of quantum computing. On May 4th, 2016, IBM launched the IBM Quantum Experience. For the first time, anyone could run their own quantum computing experiments on a real quantum computer accessible via the cloud. This sparked a decade of exploration, and today there are hundreds of thousands of users who have run trillions of executions on cloud-based IBM quantum computers. Today I'm excited to welcome two guests who've been there more or less since the beginning. First, I have Jerry Chow from IBM. Jerry has been at IBM for 15 years and was on the team that put the first quantum computer on the cloud. Today, he's the CTO of Quantum-Centric Supercomputing and an IBM fellow working to realize quantum computers at scale. I also have Travis Humble, the director of the Quantum Science Center at Oak Ridge National Laboratory. Travis has stuck with these systems also since the beginning. His 2017 paper with Keith Britt was among the first research papers published using the IBM Quantum Experience. Today, Oak Ridge scientists have run impressive molecular simulations on IBM quantum systems. I thought it would be fun to transport back to the early days of quantum computing on the cloud while recognizing just how much progress we've seen since then. So maybe we'll start with you, Travis. Why don't you take me back to 2015? What was it like to run a quantum computing experiment back then?
Well, back in 2015, it was very different from the experiences that I think a lot of people have today. The access and accessibility of quantum computers was greatly diminished compared to now. It was really only the laboratories that had invested in building their own quantum computers that had access to them. If you were fortunate, you could be a collaborator with one of these laboratories, have the opportunity to test things out. But even those experiments at that time were highly volatile and really focused on pushing the cutting edge around coherence and fidelity and even creating the qubits. So a lot of work was focused around theory, modeling, simulation. That's certainly where I spent most of my time, was trying to think about what it would be like to actually have access to a quantum computer and how would I run programs on those types of systems. It spent a lot of time thinking about scaling, how we would eventually reach scales of quantum computers that could tackle very hard problems, but our understanding at the time of what the architectures looked like, what the applications needed to be, was again much less mature than it is today. And so I would say back then, back in 2015, a lot of our effort was still very exploratory, not quite yet ready to transition over into applications and their realization, but rather kind of wishful thinking about the types of programs we wish we could write.
Totally. And Jerry, from your side, what was it like to sort of be, kind of somebody in charge of having a quantum computer and letting other people use it? Did you guys ever work together? How did you kind of offer access?
Yeah, no, I mean, at that time, I think it was very much the realm of physics laboratory experiments that we were housing, right, in these different laboratories. And, to Travis's point, it was really about to perform experiments on these machines. It was about who you knew and what kind of academic collaborators did you have, right? I mean, this dated back to even my days before IBM at Yale, that we were working with theorists who wanted to run things on like a 1 or 2 qubit experiment that we had, right? And even at IBM, as we were starting to put these devices, as we were improving the devices and we were going to conferences presenting the results on them, we would get asked, could we do X, Y, and Z on this? But, we were always moving, right? We were always trying to do something new. Like we never had a lot of time to kind of sit and say, okay, let's sit down and work on a research plan together and put a proposal in and go get funding for it to go run this experiment. And so oftentimes we had to say no to a lot of people, right? That we couldn't just go in and try out their ideas. So that was a very different time then, right? That it was very much just in the hands of those that really had control over the devices in the real physical quantum physics laboratories.
Totally. And then Travis, there wasn't like an interface for these computers either, right? So if you wanted to do an experiment, you sort of had to like hand code everything, tell the hardware folks exactly what you wanted to do, right? What was that like?
I think this divide between theory and experiment was very deep at the time, partly because of the circumstances of, just as Jerry was describing, you needed to invest in the experimental development, and that was a full-time job. This idea that you would be able to simultaneously support programming and benchmarking and applications, that was not there yet. And so on the theoretical side, the development of the algorithms and the applications, you were kind of wanting, what is this future architecture going to look like, these computer platforms? There was a lot less talk about hybrid. There was a lot less talk about integration. It was really stuck in the mindset that quantum computers as a computational model are going to provide us an opportunity to test out new algorithmic principles, solve things in interesting ways. And of course, a sudden change came, and that proved to be monumental. But at the time, this divide was very real, and the demands of the progress that we were placing on ourselves wasn't encouraging this type of collaboration.
I mean, taking all that together, Jerry, can you tell me a bit about the conversation to put a quantum computer on the cloud and start offering access to these things?
Yeah, so I think it was in one of our kind of I didn't know it then, but it's sort of you have these cycles of being able to propose new ideas and new projects, and so with Jay Gambetta, we actually in the spring strategy meeting for really IBM research at the time that we brought up this idea of trying to put a quantum computer for access through the cloud with the right kind of API and interface to access it. We wanted to get this project plan approved, get it funded. We thought about it from the point of view of wow, we keep hearing from everyone that our devices are really stable. They're very they look very good in terms of coherence times. We knew that they're stable. We decided that well, let's find a way to actually provide that to people, right? And so that's where that project really kind of started internally.
And then, so how did it actually go from being just a project plan project to something that you actually did?
So then we had to really map out what it would look like, right? And it's actually fun that maybe the first instance of that we were kind of shooting for something a little bit too big to deploy. I think the first version of charts I had, I was trying to put even like a 13 or 17 qubit processor up, right? And but then as you go through this process and design process of what you can build and what's possible, both from the hardware as well as the software side, you scope down, and then we got to a point where we were able to decide, well, this is really an MVP that we know we can reliably get and put out, and we started to execute on that, right? And so we had a team that was focused on more of the hardware side, with a team that was focused more on the software implementation and how you would program side, right? And then there was also a front end developer side, front end what it looks like to users, and all this had to come together in order to really complete that project in really a short amount of time and launch it.
And tell me if this is right, but if I remember correctly, there was some like IBM conference in 2015 where somebody got on the stage and asked if we had a cloud-based quantum computer, would you use it? Can you tell me about that?
Yeah. So that was at our then it was called our ThinkQ conference, and it was Professor Ike Chuang from MIT who polled the audience and asked people whether people would be interested in using such a machine, and it was certainly at the time we were already well into the development of this, right? So it was actually fun to see a validation that there were a lot of hands raised in terms of wanting to certainly play and explore and use a capability such as a cloud accessible quantum computer.
And Travis, would you have raised your hand back then?
Oh, absolutely. I think probably would have been one of the first, because
Awesome.
that type of opportunity was very new, right? It was something that we hadn't seen yet. So this was innovative and exciting.
Cool. And now maybe let's go back to Go Live Day. So what were you thinking, Jerry? You're about to unleash this thing on the world. What was it like?
Yeah, so go live day, May 4th, 2016. We were, I remember that we turned it on really near, it was at around midnight, and we started seeing some of these jobs coming in. It was the same time that press was going live, right? So there's starting to be articles that were also talking about it. We knew that if the platform was working, right? Because we had done sort of a media tour beforehand to show the demo of it, show everything, and it was working, working there in terms of every type of engagement that we had. But then watching the real jobs start coming in, it was kind of funny. Both Jay and I were just in the console, like looking at, is everything running? Is everything hanging? And things seem to be moving. And I think we stayed up, a couple of hours past midnight just to make sure that everything, nothing was breaking. But, and then over the next few days after that launch, we started to see a lot of people actually starting to use it and talk about it and tweet about it, and which was super exciting.
And then Travis, when did you first sort of catch on that this thing was live, and kind of what was your first reaction?
Oh, I think like Jerry was saying, it was big news for the community. And I wouldn't say that we all yet appreciated how substantial of a shift in the paradigm that it was creating at the time. But certainly within a year, people had already begun to talk about, using the IBM quantum computing systems for testing, evaluation, benchmarking, demonstrating. I mean, by today's standards, they would probably be small chips, for most people. But the truth is, they were the thing to have access to, and um, it also kind of forced that realization of the practicalities of what it meant to try to program a quantum computer and to build a bridge over that divide we were talking about earlier. I really think that one of the most significant values in this entire experiment has been that shift in the paradigm and that bringing together of the community around this question of what does it actually mean to have a quantum computer in your hands, so to speak, and to make use of it.
So what was your team's kind of early work that you were doing then, and how were you all working to bridge that divide with these early 5-qubit cloud-based systems?
At the time, a lot of it was focused around understanding the language, getting over the barriers of adoption. Of course, people were familiar with the theory of quantum computing, but the syntax of how you would program a quantum computer, the tools that you would need for that, and believe it or not, the debugging and the validation, the verification, all of those were things that had to be built as we were, kind of in the process of using these systems. A lot of our early research at Oak Ridge was focused around trying to transition things that had previously been used for quantum computing theory over into these kind of practical applications. I think the probably one of the best solved problems in the quantum computing community is the energy of the hydrogen molecule. I think it's accessible. It can be implemented on relatively few number of qubits, but the tools that you need to manage all of that domain knowledge, chemical knowledge, as well as the quantum computing interface, that had to be built, right? And the people that were building it were not, at least at Oak Ridge, were not the same ones that had built the hardware system. And so you found yourself in this kind of feedback loop. And that was maybe some of our early experiences, was understanding how to provide feedback so that you could help the next generation of device and interfaces progress. So I think in the early days, this is certainly where a lot of the attention, a lot of the effort got spent.
So really just writing down what you did, showing the challenges that you faced and how you overcame them, and then kind of passing it on to the next folks so that you can make these explorations repeatable, more or less.
That's certainly part of it. The other part of it, though, was trying to prove everybody that you were right all this time. That, once you got your hands on this quantum computer, you were going to do something that, really was going to make all the time and the effort up till now worth it. And these early demonstrations played that role. They were showing that quantum computers have scientific meaning, and not just because of their quantum computers, but because they can be used as tools for these other types of exploratory discovery processes. And so I think that that was also in the backs of our mind that, as excited as we are, we know that in the long term, the success of this program, this campaign of quantum computing, depends on how we make use of this opportunity.
So, Jerry, you have this sort of emerging research papers and folks kind of facing these challenges, things like that. So, kind of in those earliest days, how do you respond to the community writing these papers, and how do you begin growing the program in order to, sort of move back and forth with them?
Yeah, so I mean, a lot of the beginning was about kind of cultivating that community, working with them, hearing their feedback, seeing what they were running, uh, you know, uh, in many cases, even contacting people to work with them if they had certain issues that were not running through very well. Um, a lot of that went into ultimately, a lot of it actually went into our design of how to program these machines, how we, almost a year after we released the quantum experience, we actually exposed Qiskit, right? The open source software toolkit for programming. And there we were able to get another set of kind of, the start this developers journey for programming on quantum computers. And so you started to seeing like to you know to point to some of the things that Travis also mentioned. You start to see these different layers of people who are not the hardware people, right? But getting access to different parts of the ecosystem, and seeing where they best enter, right? And so we go from something which was the first time physics experiment, now exposing this is a neat way and in terms of a programming model API. And now you start to build out this new rich software stack and software ecosystem that ultimately needs to drive towards applications. But we've opened the gamut to so many more people who can now touch this, right? And so for us, a lot of that was to see that opening, hear what the community is looking for, and start to build that into both the software as well as where we could improvements to the underlying hardware and advances in the hardware in terms of a more qubit count and so forth.
And was there like a piece of research or work or something that somebody did on the system that kind of really made you feel like it had caught on, like people were doing what you were hoping and, it was pushing the field forward?
I mean, I think a lot of there's always these experiments that were like about benchmarking the devices, right? And benchmarking the devices to characterize how well they were performing, and to show certain things about like how stable they were, how usable they were. So those to me always stood out. Others were certainly, I'd say, that stood out. We're starting to leverage it to look at some of these types of like chemistry problems, like what Travis mentioned. Even those early days when people start to look at a hydrogen molecule or something like that, right? To really program like a variational quantum eigensolver into a simple five or 16 qubit quantum processor, that we started being able to see that was possible, right?
Got it. Variational quantum eigensolver being one of these sort of early early algorithms that is kind of doing one of these chemistry optimization problems, basically showing a thing that a quantum computer can do, right?
Right.
Well, and then Travis, Jerry brought up sort of this benchmarking and early chemistry experiments, which I know actually kind of the corpus of work that you all were doing back then is almost exactly that. But one thing that really struck me was seeing how forward-thinking some of the earliest papers were, that it was really things like, how are we plugging this thing into an HPC now? And, even I was really surprised almost that even from the beginning, your team was thinking about how this was actually going to be used as a real problem solver for real science. Can you talk to me a bit more about how you were thinking back then?
Yeah, the Oak Ridge National Laboratory has been home to some of the fastest supercomputers in the world. And generally, that is because we're thinking ahead, looking for these inflection points in the technology itself. Quantum has been on the list, for a long time because we know it's got very good sound theoretical reasons why it will be remarkably impactful. But the question of how do you balance what the quantum computer can do versus the latest generation of conventional HPC technology, I would say that's still a hot topic today. That's actually something that we're continuing to work on. Back then, it was even more murky about exactly what would the quantum computing systems look like and how would they integrate together. I think at the time we were very much in a GPU accelerated paradigm for how the supercomputers were built. And I remember very clearly, kind of advocating, well, let's have a QPU accelerated architecture where everywhere I've got a GPU, I'll just replace a QPU. Never mind the infrastructure and the technology compatibility or even the cost, right? It just that's got to be the best way. And I would say that over the past 10 years, things have shifted from this to a what I would consider more balanced perspective of how the quantum computers and HPC can work together. But it was important for us to try this back then because that was the state of the art. That was our understanding of computing and the frontiers of computing that were available. I think, yeah, again, having access was a paradigm shift because it really brought home what are the overheads associated with putting things together? What are the tools that are necessary, the integration, and perhaps maybe even unexpectedly, what is the language barrier to people trying to do that? We still are educating ourselves on the HPC side to make sure that we understand what it means to talk about quantum computing in that context.
Now, I actually hope to talk about this at length. So maybe I can bump that over to Jerry and kind of ask the same question, which is, back then, I mean, today, of course, it's starting to emerge in the community the importance of this quantum-centric supercomputing paradigm that we have to build these things together. But, back then, were you thinking about that also? Or how was that kind of emerging as a conversation?
I mean, it was always a direction, right, that we had as a North Star, and kind of why Oak Ridge was a great user, right, in terms of being able to leverage these types of machines and to look at how that kind of hybrid architecture could eventually evolve. But let's also be realistic that, like, at the time we were certainly working with these devices at a scale which were ones that we were running on more toy problems, right? And so to me, a big push there was really about how could we get the devices on a trajectory of making improvements and pushing them to the point that they really could go beyond what you could do classically, right? And so a big part of that was for us to continuously upgrade our fleet, right? But also to follow this roadmap where we're able to eventually get over 100 qubits for our processors. And, that I think, really did a shift, I'd say, of guiding the community to then push the envelope in terms of what could be done in terms of these quantum circuits at a more advanced level.
So you bring up the community, and I think it's great that there's sort of this there's this conversation going, right? That Travis and Jerry, your teams are trying to chart out what the future is going to look like, but you can't do that unless there's people who kind of have access to these systems and know how to use these systems. So maybe we'll start with you, Jerry. Like in the early days, you offered these for free and open access to people. So why was it so important to have people be able to access these things openly?
Because that's really the way that you grow this type of ecosystem, to me, right? Like it's already a barrier for people to see something like a word like quantum, right? That you don't want people to immediately just scare themselves away. But the whole point was that we also looked at it really as, with our whole Qiskit community, as well as how do we get more people running their first hello world, right, on a quantum computer. And if they wanted to do that, we wanted to make sure that they could, and that wasn't just behind some type of paid access, right? That's something like that should be part of their education, part of their ability to learn what quantum computing is all about. And then from there, really start to dive deeper, right? And from there, I think we've seen tremendous growth in our overall, Qiskit adoption and a Qiskit community in terms of usage of some of the underlying capabilities that we provide. And that's been really rewarding. Even to this day, we're still offering free access, right, to our most advanced machines, because that's still a tremendous starting point and entry point for a lot of the users out there.
I mean, and then Travis, sort of, as you're building out this team at the Quantum Science Center, how do you encourage your folks to start working in this new programming a quantum computer on the cloud paradigm, right? How do you build a team around it and get people upskilled and things like that?
It is certainly a very important priority, both for Oak Ridge, but I would say even more broadly for the Office of Science within the Department of Energy. Very early on, they recognized the value that having access to quantum computers would provide, and it's exactly for the reasons that Jerry just stated. You want people to be innovative. You want them to have the tools they need to test those ideas. And you want to create that community, that cycle of feedback and conversation. So at Oak Ridge, we actually started the Quantum Computing User Program as part of the Leadership Computing Facility. in order to enable people to have that access. And IBM was our first partner in this in terms of providing access to their devices so that people could test out programs. What was unique about QCup, as we call it, is that we were able to target that user base around applications for scientific purposes. So the chemistry, the high energy physics, materials, nuclear physics, and those continue to be priorities. And what was really interesting at the time was those communities traditionally had been first adopters of high performance computing technology. Uh, they had a background in quantum mechanics, quantum physics. So these ideas of accessing these systems and lowering the language barriers and enabling the tool development, it was like a ready-made group of people. And so we found that through the program, we were actually able to grow a group of scientific end users that could support and kind of sustain these ideas. And I would say they've grown as the systems themselves, have reached 100 qubits and more. They're kind of the first line of innovation in learning how to use that.
Now, this is a concept that I feel like I've brought it up on the podcast before, but it's something that I really feel after talking to so many people, which is we always talk about quantum utility, quantum advantage, right? People getting value and use out of the quantum computer. But it seems like as early as this going up on the cloud, there was quantum utility because there are researchers who can do things they've never been able to do before. I mean, and it sounds like you're saying the same thing that, these early adopters are like frothing at the mouth to try and get their hands on this so they could do the work that they're excited about. I mean, do you feel that sort of excitement? And would you kind of agree with that statement?
Yeah. So I would say that the discovery that was enabled by having access, the ideas, the method development, the numerical analysis, the benchmarking, that has all kind of fed back into the community itself. Nothing attracts a crowd like a crowd. And, it can push people forward in a way that frankly, we were not as energized and we were not as focused prior to having access to systems on a very wide scale. Um, the I think there are technical nuances for why utility and advantage probably need to be reserved for things that have economic impact and so forth. But I think your point is right that the value of being able to tangibly run quantum computing programs is extremely significant, and I think it's something that we're still kind of reaping the benefits from.
Got it. And so we're not declaring quantum advantage on the podcast right now, but but I mean, it totally makes sense that it would be, just such, again, the excitement and the acceleration and sort of honing of the research that happens once you can more easily access these systems. It was palpable kind of reading of research. And Jerry, IBM's job is to then respond to these needs and respond to this, accelerated excitement and more research and things like that. So,
Yep.
How do we co-develop our systems to kind of respect the needs of those researchers?
Yeah, no, absolutely. And maybe I'll just touch on one piece there, right, on that community aspect. In terms of value to the community, we see it in the 5,000 plus papers, right, that have been generated through using these types of capabilities, right? But also a lot of that enablement of that kind of research comes from, yes, us responding in terms of putting out better and better processors, right? So a lot of that kind of co-development comes into seeing where the needs are in terms of improvements on readouts or improvements to the underlying 2-qubit gate fidelity. So we're always, making sure that we are upgrading our devices, right? We added in, for example, dynamic circuits, right, to be able to do more adaptive circuits and to expand the types of the kind of variety of circuits that could be run. So we're always listening there, right? And then certainly from a software perspective, building for scalability and performance, right? That was a big strategic shift for us with Qiskit, especially when we pushed it to the 1.0 mark a couple of years ago, right? That we needed it to make sure that it evolved from being just the software development kit to expose you for the first time to a 5-qubit processor, to make sure that it was optimized at a level that could really help Travis and others that were using these at the scale of 100 plus qubits, right? And that kind of ecosystem feedback to drive, usage and to drive new discovery and science is something that we're all about at IBM.
What I think we're all really excited about is exactly this, is the science. I mean, 10 years later, we're at this stage where we're actually kind of pushing the envelope with these cloud-based quantum computers, and we really are entering this era that, we've declared utility. The quantum computers are actually doing things that brute force classical simulation can't, and we're almost at that point where it seems the quantum's publishing, we're publishing papers showing circuits that are really testing the limits of what classical's capable of. Maybe Travis, how does it feel to kind of look back and see that we're actually at that era as somebody whose team is kind of doing work like that?
It's really easy to look backwards and kind of see the path that got us here. This is the benefit of hindsight. If you were to go back to 2015, 2016 and ask, okay, what are things going to look like 10 years from now? I don't think I could have accurately predicted it, because the value of this collaborative development, the feedback, the ecosystem, everything that we're kind of circling around here has been to advance the field in a direction that was difficult to predict. And that we are now at the kind of the stage that the quantum computer is transitioning out of being the experiment to helping with other experiments, right? As a tool in and of itself. It probably is going to require an equally, significant amount of work to hone it, to perfect it, to get it to a stage where it can be widely adopted. But we're already seeing that happen, and that feels pretty good, because how hard and how difficult it was to adopt these new ideas, to bring these people together, develop those tools. As many times as I grinded my teeth over the last decade, I would say that it's worth it, given the what we're seeing happening today.
Before we kind of talk a bit about kind of the future and the integration here, I do want to ask if you could run us through, Oak Ridge did just publish pretty recently some results with neutron scattering, actually almost exactly defining what you just explained, using quantum not just as an experiment itself, but aiding in the experiment. So can you just give us the quick elevator pitch of kind of what happened and why it was so exciting?
Absolutely. And I should say that this is work that was sponsored under the Quantum Science Center, one of the Department of Energy's National Quantum Information Science Research Centers, in partnership with IBM, Purdue University, Los Alamos, several other institutions, where the goal was to try to validate that quantum computers themselves can be used for this purpose of creating scientific simulations. And I don't mean benchmarking the quantum computer. We've done this for the past decade, using the science problems to evaluate how well the quantum computer behaves. What has changed in this latest result, it's called benchmarking quantum simulations with neutron scattering experiments. We're now actually running simulations. These are models of one-dimensional materials on the quantum computer. This was IBM Boston, if I remember. And then comparing that simulation, which is basically time dynamics used to calculate something called the dynamic structure factor, comparing that to a neutron scattering experiment that's actually Oak Ridge is home to spallation neutron source, one of the brightest sources of neutrons in the world, that directly probes the dynamic structure factor. And what the publication shows is that the simulated results and the experimental results actually match up very nicely, which gives you confidence both in the quantum computer. This is something that we had expected going into it, but now also that the model the quantum computer is able to represent, the dynamic structure factor it's able to calculate, is in fact akin to the model in the system that's being tested experimentally.
Yeah, I mean, we sort of talk about this, Richard Feynman, nature isn't classical. You need a quantum thing to simulate a quantum thing. And this is really what we're seeing, right? That we have these experiments that are deeply quantum, probing the internal structure of a molecule. And then we have a system who's designed to simulate the quantum behavior of a molecule. So it's really like, it's happening. This is an example of it happening. I mean, it's pretty amazing, right?
Exactly right. I would say that the additional benefit is that we know how the quantum computers are going to scale in the future. That we have confidence that as they get more and more complex, the ability to access more and more complex materials, look at finer energy resolution, all of these things start to become into reach. And those are things that currently are out of reach of our conventional methods. So it's very exciting for this as well.
I mean, Jerry, this is almost a challenge to you, right? So how does it feel like looking back at that research, but then kind of now it's our job to scale, is it not?
Absolutely. I mean, that's the whole point, right? That we have runway ahead of us, and it's really about now where do we go with these real problems um to areas where we know just there's no chance at even looking at them with a classical approximate solver or the best classical only computing methods. And to me, this is precisely why we have a very public and open roadmap, right, about where we're going, both to internally align us in terms of the real technologies that need to be built, but also to be an indicator to the community of what's to come, right? And how best we can start to plan for the problems that we want to look at these different junctures as we make the next let's say Nighthawk release that increases the number of gates that it runs, or as we get to, for example, our fault tolerant systems that we're planning for later in this decade.
And so, I think folks have seen the roadmap, but where are we going? How are we continuing the vision of quantum on the cloud in the next couple years?
Yeah, so where are we now, right? Today we have some amazing 100 plus qubit devices that are our Heron and our Nighthawk devices. They're running circuits that are certainly at the scale of several thousand gates, 5,000 plus gates, and using error mitigation techniques. We're getting accurate results from them, and we're starting to see a lot of these experiments using them. For example, the neutron scattering work. There's some other papers recently that have been also pushing the envelope of what you can do on these types of machines. So we're going to continue that phase where we're going to make improvements to these devices that are available to our clients, to the cloud, and increase the number of gate operations. So we'll get to 7,000 plus gates. We'll get to 10,000 plus gates, 15,000 plus gates in the next few years. But at the same time, we're already focusing on a large leap in terms of what we can deliver near the end of this decade, which is a truly fault-tolerant quantum computer. And this will be a fault-tolerant quantum computer at the scale of 200 logical qubits in our Starling architecture. It uses a novel error correction code that we developed, which is very highly efficient. And there we're really targeting to be able to run circuits all the way out to 100 million gates, right? So really unlocking kind of the realm of algorithms and applications that people have really theoretically proven, right? Have been proving over the many years. And yet bridging also to the kind of exploration and the heuristic advantage demonstrations that we're trying to see and really enable with the near-term roadmap.
Incredible. And then, Travis, where does your work go from there? Hearing that you may in the next 3 years have access to a fault-tolerant quantum computer, how does that, what is sort of the roadmap for the actual research?
Yeah, it actually impacts the future of the research in a lot of really good ways. On the one hand, it transitions into this paradigm, the fault-tolerant paradigm, where I can start to recruit users who know less about the details of the quantum device and more about the details of the algorithm. So that separation of concerns that Jerry was talking about earlier, they become a little bit firmer. And the benefit of this is that it expands the pool of users who are going to be interested and ready to adopt the technology. And I think adoption is going to end up being an important player in all of this. But in addition to that, you can start to chart out these boundaries, these problems that we were just saying, we can't solve them conventionally right now. So we know that we can move past certain set points where that can itself spur investments in other types of instruments and other types of experiments. I'll give you a great example of this with the neutron scattering. At Oak Ridge, we're actually building a next generation neutron scattering facility called the Second Target Station. And it is specifically intended to provide us access to lower energy neutrons that can probe even finer details in these materials. In order to complement that, we need plans around the quantum computers and the applications on those quantum computers that can dig into the signals and the signatures that are coming out from those experiments. You can imagine this with many other types of devices, microscopes, imaging, you name it. The quantum computing and having these roadmaps that kind of point towards this, um, I'll say quantum advantage in this context, okay? That points towards this future of quantum advantage for scientific discovery. That's really impactful. And I think it is technically exciting, but then socially, it energizes that community, it increases that adoption, and frankly, it kind of expands its integration into our scientific methods. And I think that's a pretty cool outcome for you know the field.
Well, I mean, and then for you as a person who kind of manages users and is seeing these changes happen, I'd love to hear how you build out a team that's not no longer sort of like an experimental or theoretical physics team, but actually a team of chemists using quantum to do chemistry or researchers using quantum to do research. How do what, like if a listener wants to work in quantum computing, like what should they be doing? How do you join a team like that?
Yeah, that's a great question. And I would say that we have some experience with this on the HPC side, which as a community also goes through generations of novel architectures and device acceleration that can sometimes be very disruptive. I would say it's not quite as disruptive as the transitions we're experiencing right now, partly because of the tooling and the computational model and these types of things. But within the Quantum Science Center, as well as the Quantum Computing User Program and other parts of the national laboratories, we basically build these teams from scratch to focus on these scientific problems. The value of their expertise, though, is that they can now release tools back to the community, open source software, libraries, data sets. All of these become enabling for others that want to get involved. So if I have an application library that I have spent time developing to target a quantum computer, but I've exposed that interface now in an application library so that a computational chemist can use it, I may not be the one to figure out the next, breakthrough in chemistry, but they'll be able to use that tool, that library to enable their simulations. This, of course, happens across many different fields. It goes beyond just research into industry and other types of application areas. So I think that's part of the trick going forward is that we have to support and sustain this infrastructure that we've been building with the expectation that more people are going to need access to it in order to encourage that adoption.
And then we're kind of coming towards the end, but Jerry, I want to just hear from you, how then you, as somebody thinking about these systems, support that growing community and kind of help build it up. And yeah.
I mean, there's a big part right now of this direction that we're going with quantum-centric supercomputing. We see a huge push in the direction of those that we'll call it, HPC natives. There are a lot of people at Oak Ridge and other parts of the DOE that certainly, have that supercomputing mindset as their, go-to spot, right? How do we make sure that quantum fits into that ecosystem? A big part of our directions with Kiskin has been to really evolve the software stack in ways that can be native in terms of its usage with those types of users, as well as things such as the right kinds of orchestration and resource management tools. We want to speak the same language as the HPC users, and that will get it into their hands the quickest. I really see this, as like how the GPUs first were getting pushed for doing vector graphics and games, but who came to the bidding of really pushing it to the next level of usage? The scientific compute users, such as those from the national labs. And so we want to see that same kind of energy, right? Drive the edge of science using these machines, and we're working with them together to enable that.
I wanted to ask one more, maybe more fun question. So usually I like to ask what you're most excited about for the future, but kind of in the spirit of 10 years, I'd love to hear, just looking back over the past 10 years, we'll start with you, Jerry. What is the biggest surprise? What's kind of been the biggest shocker, now that we've gone through all this?
What's the biggest surprise? I mean, everything's sort of been a surprise to me for this, right? Like, I certainly thought that we would make a big waves by putting it online and getting people interested and excited about it. I had no clue that it would, in many ways, almost shift an entire industry. There's a whole quantum computing industry, right? There's startups, there's software integrations. There's a whole ecosystem economic entities that are relying on quantum today. And to see that and see, certainly we're happy to be in a great position as drivers in this field at IBM, but to also have great relationships with the national labs and with Travis at Oak Ridge is really rewarding.
Awesome. And then Travis, I'll ask you the same question. Looking back, you've been here basically since the beginning, managing users. So what do you find kind of most surprising that you totally wouldn't have expected back then?
I had a conversation with my wife. This was over 10 years ago when we were first talking about quantum computing. And she asked me, she said, well, what if it doesn't work? And, I think it was healthy skepticism on her part. And I said, well, it's not like we're going to give up. And I think the last 10 years has borne that out, because this has been a very difficult hill to climb, right, to get to where we are today. And I think the enthusiasm and the kind of excitement that the community has, that's not coming as like a temporary transient phenomenon. Like, this is something very real, something that is contagious, and something that we're finding is only getting bigger. So I think that's the biggest surprise for me, right? It's easy to think about this as work, right, as a professional scientist. But the truth is, there's something very inspiring to the human spirit that's going on within this quantum computing community right now. And I don't know, that makes me happy in a very surprising way.
Awesome. Well, really, thank you all for this conversation. This was really fun, and we really, thank you for your expertise, and, here's to 10 more years and way beyond, right? Thanks so much.
Thanks a lot.
Absolutely. Thank you.
That's it for this episode of the Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts, comment in the comments section, and share it with someone curious about quantum. You can find us on Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thank you for tuning in. And remember, the quantum future isn't just coming, you're building it right now.